Alrighty, live for Abna Code Day 13, 2024. We have 15 minutes, and I think I'm just gonna keep picking away at this interval class I started. So, this is an interval, much like Scala's built-in range class. And I want to have this basically so I can have these set-like operations here. I'll implement an empty interval in a minute, but I do want to change some of these definitions. Well, actually, not yet. This should return an empty interval, but I don't have that class yet. So let's start. So this, I think, has to be a class because it has the integral type class. I don't know that these are necessarily correct. Just think about them one by one. So def min, there should be no min or max on an empty interval. Those should throw some sort of error. And see, def size is going to be 0 for whatever integral type we're using. Just like that. And contain should always be false. Okay, and to range. I don't know if that works. Is this an inclusive range? Exclusive range, 0 until 0. Okay. Yeah, to an int range. And for numeric range, we just use our type. Not with these zeros, though. So to numeric range, should be a numeric range of the same type. Wait, does that just work? Does that upcast those zeros? No, it doesn't. There, it shouldn't. Okay. Oh, that shouldn't be 0. That should be 1. It should default to no. Let me see constructors for numeric range. Well, let's do this. Let's define 1. Or, let's just use our summon. So we'll summon our type class and do interval about 1. Okay. What else do we have? So we have the shift, let's expand. I'm gonna start from the bottom so I can keep these both in view. So def union with some set of intervals. Yeah. And it should just be those same intervals. To list, cool. Def union with another interval. Should just be that same one. And if you diff, it should just be this. I should put overrides here. So diff with a bunch of intervals. You move a bunch of intervals from an empty interval and you get that same one. Oh, I guess you get a list of this. I don't love that. Okay, def diff, and with just a single interval should be n. No, no, no. How's it not knowing? This is bad autocomplete. Um. Oh, wait. Yeah, it is a list of intervals. Well, if you dip anything out of this, it's just this. So I guess list this is correct. And if you intersect it with another interval, you just get this one. I guess in this case, it's none for now. Def inter. And then there's a superset of nothing. So def superset should just be false. And if you expand it, you can't really expand it, can you? Hmm. So this should throw an error. Um, I'm not sure this is correct. I don't think it should be correct. Yeah, and then shifting it shouldn't do anything. Here's a thing though. I mean, suppose you have an interval from, you know, m to n. Now you could shrink that interval, shift it, and then grow it. And that should be equivalent to just taking that original interval and shifting it. But now if you shrink it down to an empty interval, then shift it and grow it, the thing is you can't shift an empty interval, right? So shouldn't an empty interval kind of keep track of where its emptiness is so that we have that invariant? Hey, arrow bounce. You realize my part of your code needed to be sideways from what you expected. Did you mix up indices somewhere along the line? Oh man, that took me a while, but I am happy with the final result. Okay, so shift. Um, so this should be this. Right? Like if you take a normal interval, shrink it one, and then grow it one, it should be the same interval. But if you shrink a normal interval so much it becomes an empty interval, you can't really grow it back, right? So I'm wondering if that should be like we should have different types of empty intervals. Like where is it empty? Like 0 until 0. Hmm. Yes, the wall is in fact orthogonal to the direction that there's empty space. Not in the same direction as. Okay. Did you do like a walk the perimeter approach for part two? I I finally got that to work, but I wasn't thinking straight enough to make that work clearly. You would think, like, having very kind of explicit language, you could make it sound clear, but I wasn't doing that. But once I did the corners approach, that was so much easier to think about. And I never did figure out finding donut holes with a walk perimeter approach. Like, you still have to scan the entire interior, which is what made me go to the corners anyway, because then you're just scanning over the whole bounding area. So let's see. 0 until 0 is an empty range. Yeah, it's an empty range with a value. So, okay, and then that'll be, just give it the same thing. And let's say val C is 1 until 1. So A equals B, true. And this A equals C, true. Okay, all empty ranges should be equal. Yeah, I agree with that. But yeah, so those ranges do keep. It's because those are inclusive or exclusive ranges by default, whereas I'm implementing an inclusive range, which I guess I see why they made that design decision. I'm only gonna work on tonight's for 1.5 hours, maybe 145. I feel ya. I feel ya. Last night was a long one. You need your sleep. I need my sleep. I took a nap today, but geez, advent of code. Um, yeah. I can't remember. What was your approach, Michael? Did you end up doing? I think you were doing a walk around, right? Arrow bounce, not true walk. Checked for empty spaces. In part 2, I took the perimeter pieces I found in part 1, put them in a set, moved random pieces and any piece in the same line. Okay, right. I thought about doing that, but I don't know, I felt lazy. I didn't want to search for all the other perimeter pieces that were on the same line, because then you'd have to look for gaps as well. But I see, I see how it'd be easier to avoid edge cases there. Shifty 1421, thank you for the follow and welcome. Okay, so we have all of these. We need an iterator method. And this is just gonna be an empty iterator. Yeah, exactly that. Let's make sure it has the right type. Iterator of n. Cool. And we have two range, two numeric range. You had a fair part of while loops that just checked for the one directly next and kept crawling one unit at a time. Okay, yeah, just search while there's one still adjacent. Fair. Yeah, and then after that, you take another random piece, crawl up and down the line. That makes sense. Now, with these, I've always wondered about these grids where, I don't know, what if you took an alternate coordinate system? So that basically, like if you translate the whole thing over, then you could walk along the line itself instead of walking inside the line, right? I mean, let me try a whiteboard here to illustrate. And I felt like I've wanted this every now and then to a point where like maybe it makes future problems easier to try them that way. Oh, 2-minute walk, by the way. But yeah, if this, I don't know, let's say this is some sort of boundary, but your cells are like this, right? If you took an alternate grid system, like shifted everything and added extra grid pieces, like maybe you can find something that's easier to work with, right? And then at this point, you're not worrying about like your precision and direction. I don't know. Oh no, where is? Okay, 1 minute left. This is almost, I think I did actually implement them all. Cool. We have a problem somewhere. Okay. Day 13. All right. Good luck. Good luck. Day 13. Let's check the input. Oh, I like this already. Button that does something with X and Y, and then prize at a location. Okay. Law contraption. Plus a few tokens you would have to spend to win all possible prizes. Okay, so that's a prize you can win with. How do you win a prize exactly? Each button would be pressed no more than 100 times to win a prize. So, good hint, upper bound. Okay, instead of a joystick or directional buttons to control your claw, they have two buttons labeled A and B. And A and B each do different things to X and Y. Whereas you can't just put in a token and play, it costs 3 tokens to push A button and 1 token to push the B button. Okay, so you have to find a minimum. Oh, okay. So you're basically taking like 2 little vectors, and using that to find a path to a prize. This is a math problem. This is a linear algebra problem. And I am rusty, but we can figure it out. So right or forward. Each machine contains 1 prize. Okay. Okay. Figure out how to win as many prizes as possible. What's the fewest tokens you'd have to spend to win all possible prizes? Wait, what's this about possible? Okay, the cheapest way to win the prize is by pushing A 80 times and B 40 times. For the second, third, and fourth claw machines, there's no combination of A and B that ever win a prize. Okay, so we do have to make sure that they are indeed possible. And I feel like we can do that just with some math. Okay. So let's make this a list. I'm gonna parse it like 1 button at a time. So val A buttons, and we're just gonna do input dot collect. I could parse this in chunks, like taking 3 at a time, but I don't. I don't know. This is just easier to write, even if it's 3 passes. So we have x plus some x and y some y. Okay, import AOC dot point. Well, that'll be buttons, yada yada, and val prices. And it correctly guessed what that looks like. Okay. Should we press into machine? Let's do a machine. Val machine or case class. So it has an A button. Yeah. And then a prize at one location. So another point. I don't think we need any of these. But we do want list of prizes, val or machines. So yeah, we just zip these all, yada yada, and then now we have a lot of machines. So we are parsed. So first we can check if something is even possible. So let's say you had 4 and 2. You could never get an odd number, right? So I think they're only possible if they are mutually prime. Yes, I think they have to be mutually prime. So if they share any factor. Okay, def mutually prime. Import. I think we have mat.lcm in here somewhere. I thought I'd added that. Yeah, amc.math.lcm. Wait. No, we want the greatest common factor. So okay, and def winnable. Yeah, let's make a method on this machine. Okay, there we go. Each of the prime in each direction. And our prize list is empty, which means we didn't parse it correctly. Let's see. Prize x equals, right, and y equals. Okay. And it says at most 100 times. Why don't we just brute force? Yeah. I don't want to make this method because I want to have functions out in the open and testable. Okay. So no more than 100 times. I still want to do this with math, but well, let's think it over. So A always moves X and Y. What is this kind of thing called? Oh, wait, and it's always plus. Okay, since there's no minuses, that makes this easier, actually. I was thinking, I don't know, like those glass problems. You have glasses of water. You can subtract. Okay. So we could basically try and fill up with as many A as we can. And then reduce those. So let's do cheapest combo. And we have int and int of button pushes. Okay, so we start with as many A's as possible. A times from 100. And we could probably lower this upper bound to calc upper bound. So from 100 to 0 by -1. And for each of those, we go I think we can start with a small number b until we get there. So we can do an if here. If let's see. We have we can move something by a machine. Mm, so we always start at 0, 0, right? So on that origin plus MA. Not exactly. So let's say we want to check if something's still before prize. Well, before prize. Yeah. Before prize. So a point in a machine. So p dot x is less than or yeah, we just want to check that's not past the prize. And do I have a multiply on points actually? Let's define one now. Fixed def scale, linear scale. Yeah, that works. Uh, yeah, for prize. Oh, we should just give this a value. So this is the location after A. Let's call it A pause. And yes, exactly that autocomplete that showed up, whatever. Just copy paste this. Okay. So if A pause is before the prize of the machine, then we can continue and to do B times from 0 to 100. And then B pause is A pause plus M dot B times B times. Okay. And we just take the first one, right? The very first one we find. Oh, wait. This isn't necessarily going to be true about the cost-wise. Because suppose A did, so A costs 3 times more? No, hold on. Um, 3 tokens to push A. Oh, yeah. So A costs 3 times more, but But A could also move 3 times more, right? So in the case, like in this one, you obviously want to do a lot of Bs, but this one here, oh, maybe not that one there. Okay, you just brute force this. This is 100 by 100. So build A times B times. So now combos. Actually, let's just make this def. So def combos given a machine. So this is seek of int. So cost given a combo, it's C1 times 3 plus C.2. That's A and the B. Okay, so these are combos that work and win the prize. And there are like take loss statements we could have to make that more efficient if we need to, but we won't bother because it's 100 by 100 by the number of machines. We can handle that. Okay, so combos. Given an M dot min by cost. Wait, what do we actually want? It's a fewest number of tokens. Okay. Combos dot map cost dot min val as one. Well, hold on. Not quite. Not quite. So we take all of our machines, filter winnable, and then we do that. Okay. And then we take the sum at the end. Combos mat cost dot min. Okay. So just a few potential errors here. We need to recompile, I guess, the point, because it's not showing up yet. Okay, I mean, I guess we could just put def in here as an extension. Extension, and then we def this. Okay. And what is the type of APOS? That should come up. Oh, point p.x and p.y. All right. We have an empty.min. So okay, so we're having some cases. First, let's check how many we have winnable. So we have plenty. 125 winnable. Let's put this filter back. Let's turn this into a flat map so that if there is nothing, maybe there's something we didn't realize was also not winnable. Okay. And then we take the sum. 13,443. Okay. Nonsense. That means I got it right. What do you mean I answered 2 recently? What? I'm gonna assume it did like a double submit and it was actually just the wrong answer. Okay, and in the meantime, let's just test real quick. So I'll try this. So day dash 13, 2024. Save this as example. And let's play around with the example. Oh, let's see. Let's just rename this again with the dash I usually have. Okay. So it said some of these were not winnable, right? Um, so machines 0. Let's get the combos of that. Map cost. Not min. 280. 280. Yeah, that's what we saw earlier. The second and fourth claw machines, there's no combination second and fourth. So machines 1 winnable should be false. And the fourth 3 should be false. Okay. And what's the other one for the third claw machine? We also get 280. No, 200. Oh wait. Let's actually change that number. Okay, so it works on the example. 1, 3, 4, 4, 3. I think this is wrong. Okay. Kevin W. Code. What do you mean code? Okay, so it works on the example. And for the example, the answer here should be 480. I'm getting an answer 200. Okay, that's odd. So it does work individually on each of these, and it's my answer code that's messing something up. Let's just do this step by step. So filter winnable, there should just be 2 of them, right? Interesting. Is one of these not considered winnable when it actually is? Oh, okay. This whole mutually prime thing, I'm filtering out too many things. I know, I'll just... And I know why. It's because it's not the LCM of everything, or of just those 2 things. The prize location matters too, right? So it's fine if you can only hit even numbers as long as that's a multiple of 4485 or whatever. So let's redefine winnable. Winnable. Mutually prime and mutually prime. And I think I need mutually prime No, I don't think I need mutually prime at all. So for the A's, we get the GCF of n dot a to x, and we need to make sure that that's a factor. So let's say mod, or rather m dot prize dot x mod that, mod the greatest common factor should equal 0. And that's not m dot a dot x. Oh, I mean, yeah, that works. But maybe it doesn't even matter what b is. Let's say m is already a multiple. I mean, the greatest common factor should, okay, yeah, we're good. We're good. So, now x works, now y works. Same thing, and we just do x works and y works. Okay, so true, false, true, false. I found answers before 80 now. Okay, now we're not filtering too many. Okay, 36838. 36838. There we go. All right, part 2. What changes? They can go in reverse. Due to a unit conversion error in your measurement, the position of every prize is actually 1 million higher on both the x and y axis. Okay. Okay. So now we can't just iterate brute force, but let's see. Let's just take out these test machine. So I guess we have new machines, and then I guess our winnable method still works. That doesn't need to change. We don't need mutually prime. Let's just tuck this into here. So before the prize, basically we can't be listing all the combos up. Well, I mean, I still think we might want all the combos up. Well, no, we can't do all the combos at work. Okay, now we have to do actual math. This is, this feels like a shoulder problem. Hmm. So we can figure out like what mod it's supposed to be, right? Like at some point, you have to have a certain ratio of A's to B's. Hey there, hey there. You lost a lot of time to do floating point errors. Floating point errors. Really? That doesn't, I mean, I'm just gonna be doing this all like integers and modular arithmetic. So I'm curious where that comes from. You must be doing like some sort of equation multiplication. Hellhound, welcome, welcome. Have you finished for today? Let's take a peek at how I did part 1. Okay. 2,600. Well, we will have to modify the machine. So machines 2 So machines.map and the copy prize is now going to be, whoops, a new point. And it's plus 1 million. 1000. Okay. So let's just play around with this. So machines one.count winnable. It's 2, same thing. Just curious. So there are now 256 that are winnable. And again, we can't iterate. So we can approximate. So we get A as close as it can. And then we start from there. Well, no, we don't get A as close as it can necessarily. Because, well, or yeah, B rather I meant. Like, while B costs less, it might also move less. Hmm. So there's actually sort of a Z here. And we're minimizing Z while trying to get X and Y somewhere. Part 2 is challenging indeed. Am I in for a long night? And I guess it might depend if you're using linear algebra or number theory. Or calculus. Well, you could do an approximation. And then just refine the approximation. If you can guarantee, okay, is there a way to guarantee that you get closer with every iter? Well, I mean, we also want something that's accurate. So maybe we want a way to generate only accurate results quickly without doing a brute force. And then search along the cost there. Let's try it for just one of these. So let's take machines 2 and using a brute force method, which again, we could even make this brute force more efficient with bounds. Machines 2. Just take the first one. And let's check the combos. Let's make sure it's actually winnable. Just give us a value. So this is our test machine. This one is M winnable. Great. So now let's do combos. Why is that empty? This is like winning combos, right? Oh, right, because of the bounds. We could search from various starting points. We could kind of search. So a solution is probably going to look something like, I don't know, given any solution, there's going to be so, we have our origin, and then we have some prize somewhere. So origin, and then some prize. Now there's going to be a direction that is the most efficient, right? And it might be that A button is really cheap for going in the X direction, right? Even though it costs 3. So we might want like a few of these, and then like mostly green buttons. Boop, boop. So there's going to be something like this. And of course, the order doesn't matter. So every one of these is going to start basically with like kind of a long red line and then a long green line. And then at the end of all of that, we kind of adjust for how much we need to get to the star. Great. So if we could figure out that ratio, maybe we combine them into like a big vector that we add. And we get that within range. Yeah, so like what's the range where that stops mattering? Okay, so we had a 0, and let's say this was our big vector. It could be like a few copies of that big vector. And then we have like a little adjustment vector at the end. Or at this point, it wouldn't matter. There's some sort of cycle. There's some sort of repetition that's going to happen here, right? Where these are like some combination of green and red. Hmm. So let's try just to solve one. With some math. So m dot a, m dot b, and then m dot prize. Take a look at these. And how does that prize relate to m and b? Let's play around with just GCF, maybe for a bit. So GCF, m dot a. Sure, we'll just play around with the x's. And I know, let's do it. I want GCFN as well, because I want to try that m dot prize x. Okay, so in this case, they are mutually prime. What does that tell me when it's mutually prime, all three of those? Not a whole lot. Basically, you can make any combo. Ooh, I wonder for how many of these those are all mutually prime. Maybe that's like a shortcut we can use. Right. Because then we need like some exact ratio of A's and B's. Yeah. For the X, some ratio of A's and B's for the Y. Let's see, autocomplete. You can get this. Come on. There you go. Okay. So def all mutually prime. So that limits the number of A's like on the x-axis, and then like the number of Y's, the number of A's on the y-axis. So in each of those directions, well, then you have to have some ratio of those two to make it work. Well, actually, I don't know. We will work through it and get as we go. So machines 2 that for all. So are these two statements true? So this equals 1 and this equals 1. Nope, it's not always true. So let's just do filter not. Okay, so there are 163 for which that's not true. For each print line, let's take a look at some of those. Okay, so along the x-axis, wait, they would all have a common factor. How do 18 and 83 have a common factor? Let's just do a GCF of 18 and 83. 1883. What? Okay, I think my GCFN is bugged. Let's see. 1,009,765. 1,009,765. Let's try a GCF with each of those. Wait, those are all mutually prime. We filtered for ones that are not mutually prime, right? Oh, okay. It could just be that the x is mutually prime, but the y is not. So let's look at the y values. So we have 60, 58, 60, some big number, 1010902. Come on, the pattern. Nope, nope, nope. So 60 and 58, 60 in that, and 58 in that. So, I mean, these are all 2. Okay, give me a sec. I'll use the restroom. Maybe an idea will come to me. Okay. So I was thinking, um, there's got to be like a set of points that are reachable in multiple ways. And if there are like multiple ways to reach a certain point, we could take like that class of points and try to figure out like what's the most efficient way to reach that, and then basically repeat that over and over. So it's sort of like this idea I was playing with here. But how do we know like what is this set of points that are reachable in multiple ways? So for example, like if red was like that and green was like that, then every point has a unique way to reach it. There's a unique way to reach it, actually, precisely when I think, I think mutually prime matters here. Let me think. So let's say our green was up to up to and over 1, and our red was up 1 and over 2. Um, let's kind of make this lattice. In this case, it's the same kind of thing. So in this case, every point that's reachable is reachable in only one way. And why is that? Oh man, this feels like a problem where if I was a math major, I'd have the edge. Uh, um, I guess it's reachable in multiple ways when some number of greens. Wait a second. Reachable in multiple. Hold on, hold on. Are I don't know when it's reachable in multiple ways. Let's say red was just like that. No, I think it's only reachable in multiple ways when green is a multiple of red, right? Like you could have something where 2 greens is equivalent to 5 reds. Okay. Yeah, because it should be reachable in multiple ways when some number of greens is reachable by some number of reds, right? If any point was reachable in multiple, well, okay, I guess it wouldn't necessarily be some number of greens. Maybe it's like 2 greens and a red is reachable in like 3 reds and a green. Does that even make sense? I think it doesn't make sense because if that were the case, we could take out a green from both of them, right? We could take out a green from both of them, and it should still be the same. So that's like saying 1 green and 1 red. And we can take out a red from both of them. It should still be the same. Bloop, bloop. Okay, so green is reachable in some number of reds. So it's only reachable in multiple ways and therefore linear. So there's only one way for a given point. Is that right? Let's see. Let's see what happened in part one. So let's just count the combos for each of these. So let's take our, I don't know, machines that map combos of that machine, that size, dot sum, and machines that size. How many of them? 174. Wait, we're gonna count the winnable. Count winnable. 289, 174. Well, there are fewer. Winnable doesn't catch all of them, I guess. Okay, this makes things easier. We are searching for probably a unique answer for each of these. So the cost doesn't really matter. The fact that A costs 3 times more than B, this isn't some optimization problem of finding the cheapest path. And we can check that by doing machines. Might as well do 2. That for all. Let's check if GCF of it's not that exactly. We want to make sure they're not on the same axis. But making sure one's not a multiple of the other. So GCF may y and by. It's not exactly true. That's not what I'm looking for. They shouldn't necessarily equal 1. Let's say that x, so it should just be not equal unless it's 1. They can both be 1. Wait, what? You want to make sure that the A button is not merely a multiple of the B button. So we can do m.a.x over m.b.y. I guess LCM might be helpful here. GCF, GCFN, LCM, LCMN. Anyway, I'm gonna operate on the assumption that there is one unique solution. And if there is only one unique solution, hold up. I'm still caught up on this winnable thing here. My winnable method might not actually be correct. It might have happened to work for part 1 as a filter that wasn't too aggressive. Right, because there's some of these that weren't actually winnable, right? So the winnable count is going to be more than the combos count. So winnable is not actually all that helpful. Nick Wan. Oh, you're familiar. Thank you for the follow. Yeah, I've been in your stream a few times, I think. Are you doing admin code this year? Filter, winnable. Yeah, this winnable method, I think, is just wrong. It's necessary but not sufficient. Hey, thank you for the raid. So I take it this was an admin code stream you just finished. And I can tell you where I am, what I'm thinking. You're cringe? Why are you cringe? So we saw part one, basically with the brute force. So cringe. All right. Cringe raiders. Here we go. I don't think this filter winnable is necessary. Yeah, we solved part one basically with brute force. Um, we can sort of solve part two with the brute force as well, but we just give it like a decent range. Yeah. So like the upper and lower bound for A would kind of depend on what B is capable of contributing. And this only works again because there's a unique solution. And I was just like puzzling over this. And I thought the only way that there is not multiple paths to get somewhere, or the only way that there are multiple paths is if our A and B vectors are along the same plane. So I'm assuming that's not the case. I haven't proven it. I was gonna do a proof with like LCMs and GCF or something like that. I don't think it's necessary. So we're gonna take a combos part two where we just add in some bounds. And then we do a search that's somewhere near the area. Well, hold on. Yeah, so let's say we have a start location, and then we have a prize up here. We have an A and a B. So we could start like somewhere around, let's throw in some reds. So I think we can avoid doing math. It's starting somewhere near around here. And I think where we choose to start our search will kind of depend on like the ratio between A and like A dot X and B dot X. Because let's say you have, uh, I don't know, like 5 and 7 for the X's. Then we multiply those two. So least common multiple of those two. So within 35, we have like ability to adjust. Hold on, I'm not sure if that's true. Where would we actually start? Like what do we end up adjusting? Let's say we had 5s and 7s for the X values. Then if we're off on the X-axis by 35, then we can move the x-axis in that direction. Either 5 presses of the red or 5 presses of the green. Oh, and every combo that's reachable. So if we want to be able to reach everything from 1 all the way to 35, then we need a distance that's greater than that. Because we can't hit like a multiple of 6 here, right? Just 5 and 7. For example, we could hit 5, 7, 12, or wait, 10 first, and 12, 14. But if this goes on long enough, like we could hit 36. Or, we could hit 35 plus 6. So we could hit 41 by doing something, some way. Maybe not 41, but at some point we can hit everything. And I think that will determine kind of our little search radius. So it's gonna be 30. It's gonna be more than 35. Yes, I'm doing 13. Part two. Part two. And I don't know. I'm doing a hybrid. I'm trying to reason through it with math, but I need to like brush up on my math. I feel like if I was a mathematician, I'd have a huge edge here, and this could be done pretty quickly. But I'm going to do this with some combination of search. How did I solve one? Oh, I mean, there's just 100 possible for each, so I just brute forced it. Right. So A, number of times to do A, right? 100 to 0, 0 to 100. And like you could add some bounds to this, but it wasn't necessary. Yeah, so programmatically. And I think if you're solving it mathematically, you could do this in terms of a set of a couple equations, like a linear algebra style, or you can do some sort of oh yeah, this clearly won't work. Or you can do some sort of like number theory approach. Right? I wrote this winnable function, which I think is incorrect. Like this is necessary for a machine to be winnable, but not sufficient for the machine to be winnable. And if I knew how to check if it is sufficient, I feel like that would mean I have some insight that makes part two easier. Yeah, I believe it. I totally believe it. Like the part two solution will work easily for part one. But let me think. So I've reasoned through it a little bit, and I figured out that there has to be a unique solution, a unique combination of A's and B's, unless they are collinear here, right? So since there's only a unique solution, we don't have to worry about like optimizing for the cost of A versus the cost of B, because there's only one way to get to each spot. Part two. Yeah, since there's only one way to get each spot, we don't have to optimize over the cost of these two. That cost is just for calculating the answer, really. That was a bit of a red herring to me because I was thinking about how to optimize that at first. And I was thinking we could reduce the search space and do a little bit less math, like to just do enough math to get us near. But it could be a unique combination of any. So what has to be true? Let's do some whiteboarding here, some actual math. So we have A, B, and P for prizes, right? So we have and let's say we have M and N. for the number of yeah, let's say we have m and n for the number of times you push a and b. So we have a dot x times m plus b dot x times m equals p dot x, right? And simultaneously we have a dot y times m plus, I should be using like suffixes here. Maybe we could be saying xa m equals py. And oh, this actually sounds pretty easy to solve. You have an error 2m. Oh, yes, this is n. Okay. Okay. So we have two equations, two variables. Let's just solve for m. So m equals, this might actually be easier to type. So I'll keep this visible on the right half here. And let's put some comments. So a dot x times, let's say ta plus tb equals p dot x. And similarly, we have that. Now, if we want to solve for, oh no, this is for tb. Oh, hold on, the m and n are in the wrong places. This is n. It's okay, we'll fix in here. So a dot x times ta plus b dot x dot tb, and a dot x times ta tb should equal p dot y. So let's say we solve for ta. ta equals, that complete looks good. All right, subtract the bx and then divide by a dot x. Okay. And I'm going to try and do this in such a way that I can avoid, I know there's like an integer answer. I'm going to try and avoid float. I want a floating point error of some sort. And now you can plug that into the other equation here. So a dot y times ta, which is now in terms of tb, right? Oh, hold on. It's just this bit. And now we solve for tb. P dot y minus, I want to do this in steps actually. Let's do this in steps. So I can feel like I'm verified here. So a dot y times p dot x over a dot x. Okay, so those are both over a dot x. And then, so a dot y times, geez, let's do this differently. Let's say a dot y over a dot x times p dot x. So we have the same factor here, minus times b dot x times tb. Um, solving a system of two equations is totally fine. I don't know why I shied away from it. I know why I shied away from it. I shied away from it because I thought it would involve like a Z or cost optimizing um, as well. And that scared me a little. Okay, so let's see. We can just multiply everything by a dot x. So a dot y times p dot x minus a dot y times b dot x times tb. In fact, like one way we could have written this. Okay. We are just gonna move this a dot x. So times a dot x here. And then we distribute a dot x, b dot x times tb, b dot y times tb. And since we're solving for tb, we can move these bits over that don't have the tb. Hold on, let's just keep the bits that do have the tb. Okay. And what else now? I think we pull out a tb. So yeah, tb times, pull out this tb. Okay, and now we just divide. Ooh, checking my math. Forget to multiply x dot y. X dot y. Did you mean a dot y? Let's see. A dot y. Let's just look at this over. So first thing we did was move over the a dot x. Oh, right. So we moved it over the a dot x from here. We forgot to multiply it in here. You're right. So b dot y times tb times a dot x. Okay. Times tb times a dot x. Same kind of thing. And then we pull out the tb. And now we get, this is not very legible in this text format. So AB plus by times a dot x. Okay. So this is our final answer. And we do have to worry a little bit about, well, okay, this should be an integer, right? This should be an integer answer if it's solvable at all. And unfortunately, my solvable method is broken, so I can't just filter those out. So I'll have to check that the result of this is an integer. Yeah. Okay, let's just use that. I mean, no. TB, if this is solvable, TB must be an integer, right? Like this equation isn't always going to yield an integer because it's not always going to be solvable. So I just check that this is that mod is 0, and I think we're good. Okay, and then we can use TB to solve for TA after the fact. Okay, we've got a raid. Want TV? Welcome, welcome. Um, so I assume you're doing admin code. I'm doing part 2 still. Part 1, I just brute force it. It's pretty fast to write that way. Part 2, I just now did solve for the number of times to do B, system of equations here. And I'm going to plug that into, I don't know, into some method. So def solve some machine. Option int. Okay, so this basically just copied, holy shit. It copied this TA, I'm not sure about. TA was in terms of TB. Price.x minus b.x times TB divided by a.x. Okay. But we don't want to do just that exactly. Let's make this an option. So, well, let's say the numerator. And then val, we'll just call them n and d. So here's the denominator. You think you see a typo in line 119? Ooh, possible. I mean, this is the kind of place where I do appreciate backseating, as just p.x minimum plus b.y times tb. It shouldn't be, yeah, b.y times tb. Oh, yeah, this is just the a.x that's missing. But we can add for that in the next line. So I think the rest of it's good. So let's do this option.when n mod d equals 0. We do n over d. And am I going to have to worry about longs here? Yeah, we're multiplying like, well, no, this number should be less than 1,000,000. Okay, if this doesn't work, I might have to like go through and just replace all ints with longs. Yeah, I might have to do that. So that's our TA. And it's going to be in a for comprehension. So for TB from, I don't know. Can we do this? And then TA from, oh, oops, wrong direction. TA from this, again, if it's divisible. So that's in terms of TB. So val n, what's that? I know I could just do this with a float. And then there's like is integral, but I'm worried about rounding errors. So this is my way of avoiding that. Okay. So there are those two. And if we have those two, we're going to yield TA to TB. And actually, we can just do the cost. So we'll call this cost 2. And it's going to be an option of int. Let's just try to make it long here. I know we're going to have to change to long. So for that, we're going to yield TA times 3 plus TB times 3. And then now we can take machines to flat map cost 2. What's with this? Weird autocomplete. And then just sum. Found in int. What is TA? TA and TB are an int. Oh, wait. Plus, okay. Oh. That's interesting. Let's see what that's for machines 1. We take it. That's not the kind of bug I expected to get, to be honest. I mean, while we're here, I'm just going to change int to long. So dot to int becomes dot to long. And then we have our points don't have. That doesn't work. Our points only work on ints. Okay. So we're just gonna have to like 2 int in all of these. Well, these aren't gonna be too big. It's gonna be 1 million times. I mean, 1 million times 1,000 is still fine, right? Well, actually, 1 million times 1,000 is getting close to our limit. Okay, so anytime we do prize, we'll do that. YX. I don't think those are going to get too big. Not too long. And I know, let's put it too long here, set it all long. So makes it less readable. But now the question is, why are we getting a 0 here? Let's just double check our equations. So here's our original system with 2 equations. Right. And that equation looks fine. Let's see if Copilot can autocomplete. Interesting. Or yeah, let's solve for TA. And then TB equals. But now you place TA in there. And then now in here, we solve for TB. Oh, we didn't need to be solving. No, we just place TA into the second equation, a dot y times that. And let's see how autocomplete does. TB equals, it doesn't realize that I'm trying to get this value. So never mind. But this final equation, So a dot y times p dot x minus a dot y times, well, hold on, just start here. This is our TB. I don't know what's going on here. This I trust. P dot y, a dot x minus a dot y, p dot x. Or a dot y times b dot x plus b dot y times a dot x. Okay. And when n mod d is 0, then we give back n dot d, n over d. And ta times 3. Why would tb or ta ever be 0? Surely neither of them are negative, right? Just add some assertions here. They should never be negative. I don't know, ta is greater than 0, and tb is greater than 0. And let's just do cost 2 of machines 2, just the first one. And we get a none for that. So let's see this. So machines 2 at index where cost 2 is non-empty. Oh, it's just showing up none. Oh, hold on. Let's see. It's the sum of an empty list. That's why it's 0. So this is always yielding nuns here. And why might that be? So let's just try it with the first one. So I don't know, let's print line, let's print the machine. And then let's print n and d. And just do that in each of these. See what's going on. So when you do this in the first one, here's the machine. We get this n and d. And I guess those are not multiples. So 2440996 divided by 10223. Does this set of equations have multiple solutions? No, I don't think it does. Because it's 2 linear equations, right? Should have done it up in here. Yeah, it's 2 linear equations of 1 variable each. So there should be one unique solution where they intersect. And we could do that by setting TA or replacing TA in one or the other. So maybe this one's just not solvable. Let's keep trying this for a few others then. I don't know. One, the second machine. We get a negative number. Oh, fuck. Okay. That's what's happening. Let's just turn everything too long. Um, I should do some sort of find a place here. This is so gross. And yeah, let's try that again. So for this machine, we're still getting a negative n. Maybe that is actually negative, which means there isn't really a solution here. Right. That's saying that we we intersect somewhere behind. So n mod d equals 0. Let's also just check that the signs are also 0. And mod's gonna be weird with negative numbers. There are like a couple different ways you can define negative mod, and I think this one doesn't work the way I want it to. So let's check something. 7 mod 5, and then, well, I mean, that should be 2. That's negative 7 mod 5 and negative 7 mod negative 5. So they're both okay. And what if just a denominator? All right. The problem is, like, if we have negative 7 over negative 5, then that's fine because n divided by d is going to be a positive number. Let's just filter. Let's add a filter on here to make sure it's positive. Dot filter greater than 0. Okay. Now this still isn't changing anything. We still have 0 answers. Oh man, what's wrong with my equation? So I know these are both longs. Okay. I think at this point, like, I don't think there's something the what this probably is some sort of error or in the equations themselves. Like the equations did look fine to me, but let's write them out. And I think when we're drawing, it'll be nicer than typing because we can like cross things off and whatnot. So what are our equations to start? Okay. So the prize x location is I'd call these n for the number of times. So number of times you pressed A times x of A plus number of times you press B times x of B, right? So py, same thing. Number of times you press A times ya plus nb times yb. Okay, and we want to solve for NA and NB. So let's solve for NA using this one. So NA is just going to be equal to PY minus NB YB over YA, right? Such a nicer way to write things. And then to solve for NB, we're going to use this other equation. So using these two, we have px equals this whole NA. So I think I can copy paste. Hold on, cancel that. Oh, no. So duplicate. No. Okay. So we have NA times XA. Plus NB XB. All right. Looking good so far. And now we want to solve this for NB. So again, let's just copy paste this whole thing over. Okay. And now we're going to move things around. So we're solving for NB. We can pull this out. Oh, hold up. Not quite like that. Let's see, we move this YA. So we're gonna move this. You just have to drag it with the mouse. To here, and we copy it. So basically multiply everything by YA. Okay. So now we don't need that divisor bar. Great. And to solve for NB, we can move that out as a factor. So I'm going to erase this one. Just draw new parens. So NB. And then we just move that over to divide. So now we have YA PX over py. This is right, right? Yeah. Hold up. I think I missed something. There's a parens here with this xa. So it's just, I don't know, loop these parens. Okay. We have yapx, right? On top. yapx over pyxa minus yb. I should be saying by, shouldn't I? Okay, whatever. Yb xa plus, you can't take nb common. Pi does not have nb. I know you're making a joke. I can't think of what nb means. Oh, wait. Hold on. That's not a joke. That's not a joke. There's bad math in here somewhere. Okay, so what do? We move ya here, right? And then that means we multiply it here too. Right, so we have, I'm just gonna rewrite that again. Wait, no, yapx is fine there. Then we had ynbxb. So ynbxb, which the nb is already pulled out here. So ynbxb. And then now this whole thing was multiplied by xa. Was nb actually in there? Right, because we got na. Let's just double check this. Na equals py minus nbxb or nbyb over ya. Okay, so I'm happy with this bit, so that's good. Py minus nb. I should have done like crosses instead of like red slashes instead of cutting paste. So py minus nb. No, nb's been moved out. We can't take nb out that way. Okay, I see where we messed up. Can't take out nb that way yet. So I'm just gonna move over. I don't know. Let's just delete all of this. Okay. So in the next line, we multiply everything by ya. So ya px. So that gets crossed out up there. We now have py minus nbyb times xa plus nbxb. And again, it's also multiplied by the ya. Okay, let's find this. Jeez, this is like high school math. I'm being so slow on. Now, we're still trying to pull NB out. Let's just distribute this XA. So we have the same thing, but this becomes XA PY minus NBY BXA. This factor is just going to be moved over there. So what we actually have is YA PX minus that factor. What's this hand? I don't know how to. No, my tools are gone. Okay, so it's minus that. And I guess it equals. It's minus. Where's my pens? Okay. Minus XA PY equals NBYB, or is that? I think that's a YB, no, XB. XB YA minus this factor. So NBYB and then XA, right? So now we can pull out NB from both of those. And the answer that we get is that over XP YA minus YB XA. You know what? I think you can. I don't have any pride there. I'm not a mathematician anymore. But in the meantime, I do have an NB, which is this. Let's see how that compares. Yeah, sure. Matrix form linear equations. Yeah. I know. I know that exists. I don't do that because I don't remember. I don't remember how. I mean, I suppose like I could look it up here on the spot and just do it. But I do have an equation. So let's see. We have prize x times ay long. So it's the same thing as just negative, right? So prize x ay minus xap. It's just negated, which is totally fine. Surprise y x long. Surprise y ax, and then ay prize x, right? Prize y ax, prize x ay, and on the bottom it's xbya and ybxa. So ay with bx and by with ax. Geez, so I just did it twice, and that still looks fine. Doing that handwritten, I thought that would be faster than it was. Sorry for the pain. Okay, and let's say we did like -14 mod 7, right? Like they both end up negative. That should still be 0, right? Cool. I mean, so we only care about the case where it's 0. Um, Maybe this shouldn't be a 0, but just a map absolute. Actually, no, when we're dividing, that should cancel out properly. So it is positive. It should be. Okay, it could be that there's something wrong with our TA, which again, like TA, we'd solve for, here we call it NA, right? So what is this? Prize Y, NB, YB. So the number times we do B, TB. In this case, it's TBXB and prize X. We just switch the X's and Y's, but that should still be fine. I think we just did the replacement in the opposite order. And AX becomes AY down here. So we just switch the X's and Y's, and that's fine. And we also flip to like the negative sign. Okay, so geez, that equation is right. Right? Like I'm pretty sure these equations are right. Let's just see what happens when but the problem is those never seem to be something that's like nicely divisible. We are never even getting to the TA calculation because the B calculation is always okay. I feel like I'm potentially missing some sort of factor here. Right, like it should be the case that I know A times TA plus B times TB equals P. We can do this as a check. Equals m dot p rather. So these are all m dot. I could import these out of the m. It'd make things easier to read. Import m dot star, or rather, let's just make it explicit. We're getting a b, and let's do prize. Let's re-import that as p. So let's replace prize. Whoops. Prize with p, and hold up, we looped around. Okay, and then just m dot with nothing. Okay, that's at least a little bit easier to read. Prize is a point. What does it have? What's the issue here? Um, oh, right. You should put the assertion right here. That will only really come into play later, but it's a check to make sure that things are correct. TA long required TA int. Right. Because our point doesn't have longs. You should just define a new point instead of importing point. Just get this out of the way real quick. Point Scala. You don't really need anything in here besides a plus and minus. So case class point x long, y long. Okay, now we don't need to import that. And then we can replace to int with to long. And yeah, we can just delete too long everywhere now. Great, so that should be compiling. And now the multiply, def multiply, let's make that a long and take our extension def. We don't need this anymore. And we don't have point origin. Let's just get that out of the way. So object point val origin equals 0.00. Okay. And I guess we were still looking over these. For some reason, none of these seem to be kind of exact matches. Let's print along with those what it is when we divide, turn it into a float, see how close they are. Because they should be like, they should be really close. Or, we could just straight up return, I don't know. Let's re-implement this with doubles. Yeesh. So let's take this out. Val TB equals, and we don't have this filter anymore. So n dot to double over d dot to double. And then our search should still be fine there. Or not our search, I guess it's now a filter. So val TA and we just do the same thing here. And now maybe these two assertions are still valid, that they're positive. But no, they won't always be valid. So this is now like, these are whens, I guess. So when we want to make sure they're both whole, tb dot is whole and ta dot is whole. And I don't know about this for now. But we'll add these two as conditions. So when we have that, then we return ta dot too long. Oh, tb times 1. Okay, that's a bug here. It should be tb times 1 up there too. Okay. Now let's just try this with cost 3. See what prints. So we still have 0 that are valid, but now we can look. Yeesh. I want to print more after that. So what else do we want to print? We want to print what TA and TB are. Okay, and none of these are looking like they're like super close to 0 or something. But let's also do a check. So let's do a times a dot x times t a. So this is a x of where we end up. Let's just put that whole thing in the equation. So and we do the same thing for y. Okay, let's take a look at those. It should at least be close, right? To the original machine points. Are we printing those? Okay, so x is 4485 on the dot, and y 6188. Y is off. So x is correct, y was off. Here again we have x is correct, and again we have that the y is off. X is correct, y is off. Okay. Let's take a look at our x and y and where they come from. Right, so this equation here is fine. By times the number of times we're doing b. But hold on. We're just doing this for the original machines, right? Oh, I mean, so we can compare. Yeah, we can compare this against our original cost function. Uh, so cost of the machine originally, cost of the combos of the machine, def combos, right? You return to seek when there's actually only one. Um, Combos of the machine, dot head option, get the cost of that. And I don't know, for each of these you want to compare. Well, if there's a combo, we don't actually care about the cost. We just want the solution. Um, this is A and B, right? A times, let's say NA and NB. And then we can compare the cost of that. I guess it's a for each now. So cost of NA and B and the cost 3 of the machine. Okay. Let's just take a look at that for now. On. Oh, right, this is dot map here. Okay. Oh, missed our dollar sign. Okay. 147. None. Sure. Okay, it's printing something. Now what we want to do is get what the actual answer was. Let's just print line N and B. NA and NB. Okay. 86.99. So the answers we're getting are not even close because we get TA 37 and 40. Um, which means the cost is, wait, how is the cost going to be 147? It's just 3 times 1 times the by the other, right? The first bit times 3 plus the second bit. Wait, is combo just all the combinations? If B pos equals M dot prize. Yeah, right, the position at the end. I mean, we can make that assertion. We could test it real quick. Oh wait. No, the original answer is 20, 27, and 66. So this is still not 27 and 66. Right, A699 is for the next series. So like 27 times A3 plus 66 times 34, right? Or 66 rather. Is 4485. But we are also getting a 4485 somewhere. And yeah, let's see if you multiply x that many times. I mean, there is only one solution, right? There's only one intersection of these two lines. This is high school math. I have to find the intersection of two lines. I can do that. We don't really need to print that anymore. It's just kind of noise. PYAX, AYPX. And check that it's. Let's at least check. Oh, we did check the x and y. When you multiply by the number of times, let's check that the x and y is close. Right, the y was never close. The x is always kind of spot on. But the x is based on a bad there's like a bad TB value, and we're using the TB to calculate the TA. We could try solving one of these by hand, just plugging in the numbers. It's, I mean, it's a little bit annoying. But we could see where these two approaches end up differing, right? Yeah, let's just machines that take one. And let's just not worry about all this stuff that prints too much stuff. Let's take out all this testing code. That was just testing code. I was just exploring. We don't need that. Right. That's not just exploration. We don't need that. You do need machines too. But ands one, we're going to comment out for now. Actually, I don't think that'll make noise in our output. Just copy the worksheet output and let's put this in a Scratch file. Oh, copy worksheet output, Scratch. And if this fails, I'm just gonna go like look up the page on why is it going over all the machines? I'm supposed to be taking just one. Here, all this test code needs to be deleted and sent away. Okay. Here's A, here's B. Let's just see what this looks like, see why we're getting kind of different answers. So we have an NA and an NB. So it should be the case that, well, NA is 27, right? So let's make it light. So we have 27 times 83, right? 83 plus 66 times 34 should equal 4485. Okay, and our x values are fine, so I'm not too worried about that equation. Let's check the other equation. So again, y values is 27 times 59 plus 66 times 99. 8127. And now when you're solving for, I don't know, NA and NB, let's look at what that equation looks like. So let's start with TB. So we have 66, according to this. You know what? I still kind of want to do this, but I should Wikipedia. I should Wikipedia just doing the matrix thing. If you're still here, and I haven't scared you out with my obstinance, I think I'll take you up on that. But anyway, 66 is TB, right? Where we had the prize Y location. So that's the 8127 and 4485 times AX and AY. So here's AX and here's AY. 83 and 59. Um, we could print what each of these equations are actually. Let's do that. So print line. And I guess we take each of those, we just wrap them. So we know what we're multiplying. Right. And then print line, same deal here. A dot y, b dot x, b dot y. Okay, let's put that in our actual code. And do a similar thing here. Let's put those closer to what they're actually printing. Okay, same equation and print line. Nope, nope, nope. Print line here. Over dot x. You know what? I feel like our TA is probably wrong. Right? Well, no. The thing is, our TA and TB work in such a way that the x's work out all right. Okay. So here's the equations we're calculating. And what is this? So we have our TB. Yeah, let's just print the N and D after that. And do the same here so we see what we're doing. Print the N, print the D equation. And this, I think I'm just printing the wrong thing. Yeah, I'm just missing the curly braces here. Right, so this should be 66. N over D should equal 66. D times 66 equals N. N should be a multiple of 66 somehow. Right, this works because we find something that is a multiple of 66. Okay, I think the equations are just bad. Let's solve system two equations matrix. And they're each equations of two variable. I don't know, like, where I'm failing on that substitution. It's just basic substitution. Hmm. Okay, for system of equations, and let's see, mm, it's this here. So these are the coefficients. Are these in the right order? Okay, so the coefficients of x are in the first row. Yeah. NA, well, not quite. So we have to reorder this. Right. So x minus. So we have an x. We have a y. Wait a second. Oh, I'm mixing up the x and y's because the x and y's are actually the coefficients here. So NA is our x essentially. So NA and B, right? NA and B. NA and B. Coefficients of. So these are our y's. These are our coefficients of the y, which is xb and yb. Why are they both coming from the b button if they're coefficients of the y's? Are these equations even correct? So the position x of the prize is going to be number times hit a times xa, number times hit b times xb. So if NA is our x, I don't know. So whatever, we'll just put these values in the matrix, right? And then the constants px and py. And then right, each has an augmented matrix. Where did the z come in? Oh, hold on. Yeah, so that is the augmented matrix. And then row operation matrix. Right, so this is where we like keep subtracting one row from the other until it's like 0 or something like that. Coder 2K, thank you for the raid. And yes, good morning. Good morning. In what time zone? I'm just remembering how to do, what's it called? I did this with the matrices last year for problem 24, where it was like a 6x6 matrix. Good morning in Germany. Oh, all right, alrighty. Well, I am on the east coast of the US, so it is technically morning here, or a very late night. And I think I can do this. I should be able to do this in half an hour. So, row operations multiply row by what exactly? And then we keep track of like how many times we subtracted one row or another. What's this called? I just want to look at the Wikipedia page. This site isn't the best. Some sort of reduction matrix. Just a AOC. Good, good. I am having fun. I'm disappointed that it's taken me so long. So I did this without the matrices. I rewrote the equations. Something's wrong. Must be wrong with my equations. I don't know. I rewrote it twice, like once in code, and then once here on the whiteboard. And something is wrong with my equations. So just so you can read this, yeah, I re-implemented it because I don't know. Just so you can read this, we have P stands for surprise, right? And we have A button, B button, and T is the number of times you push B, and TA is the number of times you push A. So my equation here, numerator, denominator, this, I think that ought to be correct. And this is what I have for my TA equation, right? Where I just did a lot of substitution. And I don't know if I did substitution in there wrong somewhere, or I'm having trouble with like integer floating point types or whatnot. I decided I'm just going to go and do it the matrix way. Okay. So given a machine, let's find its cost. Speedbill fetcher. Thank you for the follow. Okay, we're going to define a cost for. What approach did you take, by the way? I guess you have to do a mathy approach. I suppose you can do some sort of clever search if you did a little bit of math. I don't know. I think we just want to get a solution. Let's just get the solution so that we can play around with it. We won't calculate it right away. Say solve. So if there's a solution, you will return a tuple of 2 longs for the number of times you push A and the number of times you push B. Well, yeah, plus invalidity. What do you mean? If you can tell me a line number, I can probably answer your question a little bit better. Oh, I'm going to turn off Copilot here. And for reference, I'm going to check. I think I did this day 24 last year. So day 24, Abnico 2023. Okay. And here we had X, Y, and Z. So a system with 3 variables. Start candidates. Oh boy. Yeah, this was a day. Gaussian elimination. Okay, Gaussian elimination is what I want to do. So I implemented, oh boy. Yeah, that was quite a day. I implemented Gaussian elimination for the array last year. Sixth line in def cost 2. Okay, 1, 2, 3, 4, 5, 6. Why do I have plus? Um, is that not what I have like on the whiteboard? Because that's what I got when I solved the equation. So like one's the numerator, one's the denominator. Should it be a minus? Just find my bug. You're right. Okay, let's look. Let's look here. Oh my god. Yeah, it's always differences. Wow, good eye. Good eye. Okay, right, this is what it should be. Some sort of I think you got it. I think you found my bug. Okay, it wasn't that my math was bad, it was that my transcription here is bad. So I was like redoing my math, trying to make sure my equations are correct. I didn't even write down the correct equations here in the code. Okay, well, let's try this. Let's try this real quick. Such a good eye. That's awesome. Good catch. So, just take our original machines and get the cost 2 of each of those. And we're still getting 0 solutions. But I've been kind of eyeing this one suspiciously too. So p dot x minus b dot x times tb over a dot x. Okay, so before I go implementing some kind of Gaussian elimination, let's just double check our equations here. So NB, right, NB is a common factor in here. I think I'll remove this XBYA. Right, so I can red pen cross these out. Oh, whoops. Nope, not all of those. So crossing those out because they moved, right? And now we can replace that in the original equation for NA. Oh, wait, I mean, we don't replace that in the equation. We already solved for NA here. And now we just plug in NB. So I did the substitutions differently when I first wrote this and when I retried it here on the whiteboard. So I'm just going to change everything as I go. So we have p dot y. Does anyone here use Scala, by the way? Rise y. Hold on. Let's say ay. I know these are wrong, so I'm just going to delete them. So we have a dot y times p dot x minus a dot x times p dot y, right? The denominator is oops, b dot x times y, or a dot y, minus, I hope that's a y, y dot b times, or rather b dot y times b dot x. Okay, and if we change that, we also have to change our TA. So p dot y minus b dot y times tb over a dot y. Right, is that weird that only has a bunch of y's? So py, when you solve for it, yeah, right, it's fine. It should have y's because we solve for n, na, and the y's. 174. Ah, okay. Hey, there. So this should be the same as answer 1 right now. So if we just do dot sum. Oh, he just. Okay. Q23. 20. You just allowed me to go to sleep tonight. Which means uh maybe tomorrow night I can actually show up to one of these, not sleep deprived. It's already a busy month without having a code. It's like a bad positive feedback loop. You know, the less you sleep, the longer it takes, and the longer it takes, the less you sleep. So, for part 1, 3, yeah, that was good. So now we just do this with machines 2, and that's our ands 2. It doesn't seem to work for our machines 2. So now ands 1. Let's do the size of this. Do we have anything? Actually, let's do this a check. So ands 1 should equal cost 2. So this is working for machines 1, but it's not working for machines 2. Let's do some looking at the print lines. Oh, what did you say? Never used Scala before. You're learning Kotlin for this year's AOC. Yeah, I've used some Kotlin. Kotlin was disappointing going to it from Scala, but going there from Java, I think it'd feel great. Do you use the arrow library? Matrices do the same since the determinant of a 2x2 matrix is essentially this too. Oh, okay. Oh yes, increase in difficulty. I feel like sometimes he gives us a break and we have an easy day, so we don't burn out. Okay, so we have an. Is it because there are 2 negatives? Let me just try multiplying that. 244,09926 over 6211. Yeah, that's not close. From C++ to Kotlin? Oh yeah, I'm sure that feels great. I know. I wish they had different leadership or direction with the Kotlin language, because they're like explicitly avoiding things and saying like, oh, we're not gonna do, like nice feature that functional languages have. The fact that it doesn't have pattern matching, and now like there's a sort of pattern matchy type thing. Now Python has pattern matching. Uh, Java has pattern matching. That's better than Kotlin's. Kotlin still doesn't have real pattern matching. Uh, Kotlin's is just basically a switch case. And just other bits here and there. But I did enjoy using Kotlin. I do like some of the I don't know, like the in or I like some of the language features. So I thought about like kind of porting them over to Scala. Some of like the utilities. I think you might have to do it as like a compiler plugin in Scala or some sort of macro to get some of the same functionality, but it'd be interesting to have them there. Oh, and you know what? I did like the coroutines. Um, okay, what do you want to take a closer look at here? Because we're not having any kind of integer overflow, right? So these are all longs. Okay, so this isn't an integer overflow issue. Um, we do filter that's greater than 0, but that makes sense, right? We don't. They're all going to intersect somewhere, and if the intersection is negative, then it's yeah, not going to help us. Wait, hold up, hold up. Yeah, system of two equations. It could have an intersection at somewhere negative. And the number of times you do B. Um, wait a sec. What do I want? Oh, what do I want to debug? I could do. I could do the multiplication. So the thing is, this isn't even close to. Okay, this is why I implemented a cost 3 earlier. Was because I wanted to go ahead and multiply these anyway. I have this filter. I suppose I could make it just true. Let's just delete all this. Yeah, let's just delete everything else. Okay. We're just going to do an implementation here for the purpose of debugging. And we're not going to have this filter. We're just going to make this true. And we're going to do that to double and see what kind of answer we're getting. And I know we're going to return double the number of times you push each button. Okay. So again, we're going to make this one true. Actually, we just copy paste this. We still filter for positive bits. Now, we can't multiply a point by a double. Not yet. Um, Okay, so we're yielding that tuple. Now let's do TA times, well, hold on. We want xa, or a dot x times TA plus b dot x times tb. Is Scala pure functional? No, you can write pure functional. The thing is, Scala is a very flexible language. You can write Scala that looks like Python or Java or even JavaScript. In fact, when you're writing Scala JS, often it looks surprisingly like JavaScript. Okay, so this is our x calculation. So let's print this equation. Okay, and val y. Oh, let's turn on Copilot autocomplete. You know what? Maybe it's Copilot's fault. So a dot y. Maybe Copilot threw in a plus there. And I burned myself. Right, like GPT is not known for being great at math. Yeah, so you can treat it like a statically typed Python. I know I want to do an exercise someday. Basically, you can try and say a lot of things one for one if you're using like Python iter tools. When I used Python, I really loved using iter tools and func tools. This syntax with the indents and whatnot is Scala 3. So Scala had its own 2 to 3 move in the last few years ago. I know, like 4 years ago now. And part of what they did is allowed an indent syntax. So let's write equals y and equals x. Okay, so we check those. And now we take machines2 dot map cost3. And as it does all of those, yeesh, you get some debugging. Okay, so we have this machine. We have a 3 times that equals something that's very close. Hey, that's good. These values look good, actually. Okay, in that case, so if we round it, that's probably fine. Yeah, so the equations are definitely good. The values we're getting are good. They are close. N and D. Right. This N over D. Well, this N over D gives us TB. We should print what TB and TA are, actually. Let's just do that real quick. TA and TB, there we go. And actually, maybe we do that in reverse order. So TB and TA. Okay, so TA is this number. Well, okay. That's still not valid for us. We still want an integer solution, right? Like this comes close, but we rightfully discard that because I mean, yeah, okay, that should work because the equation works. But we rightfully discard that because we can't half click a button. So maybe there's one where TA and TB are really close to a number and we're just not rounding. Okay, I could search for one where TA and TB are close. We could do an if. Let's see, there are rounding utilities. Um, that round within like 100th or something. Wait a sec, let me just think about this a little bit more. Um, okay, the solution here. Yeesh. Yeah, like we do get correct answers. I should do this on the example, actually. I should totally do this on the example. Um, one sec. I don't know why I haven't done that yet. Okay, so a machine where A goes 94 and 34 is only possible to win a prize in a second and fourth claw. Okay, now we know which ones should work. So the first one shouldn't work. And we're cool with that. Now let's look at the second one. N and D looking very. Okay. Seriously, what gives? Why is TB? We're pretty confident that our equations are correct because this works on the original machines. Right? Let's just try this again. So machines 3.flatMap cos3. We should get, oh, wait. Original machines. So we should only get two answers, right? Yeah, and those two answers are both, well, okay, there are two reasonable answers in here. They're both like 0.0, and we can say like dot hole on those. On the second and fourth claw machines, I'm getting answers on the first and third. I'm pretty sure. Unless I like parse them backwards. It doesn't tell us what the answer was. It just tells us that two of them had an answer. So for this one, TB and TA, I had good answers for plus 94 and is admin the code is is this wrong? Did they mean to say first and third? Now it's only possible to win a prize in the second and fourth. We had the same machines in the same order. Okay. I was hoping that this would show actually a bug in all of these and show that none of them work. But now it's just showing me that it does work just fine. On these examples, so it doesn't give me a thing to debug. Right, this works. This doesn't work. And this here does work. TB is A6, TA is 38. Oh, hold up. That's because this is on the old machines. Right, and it works fine on the old machines. But on the new machines, with bigger numbers, now the second and fourth should work. Yeah, I was just doing the wrong set of machines. Okay, so this one should fail, and it does fail. Now this one here, machine 2666 for A. For TB, we get this value. And we get that by dividing that by 3876. Is it possible? I don't think it's possible we're getting this is part 2, yeah. I don't think it's possible we're getting an overflow. Right, like for n, what's our equation for n? Oh, and we have it right here. Right, so a dot y. And we are confident in these equations because they work for the original machines. So I'm going to look at the second one. So a dot y times p dot. Wait, are we flipping these somehow? Oh, no, this is our check that goes back. I do also want to check what those equations actually look like, though. But it's going to be a dot y, so 66 times p dot y, 66 times a million, basically. Or times p dot x. Yeah, it's still times basically a million. So you basically have like 66 million minus 26 million-ish. Which should give 40 million-ish. So that seems right there. Right, again, should be pretty confident those equations are correct. Well, just why is it that when we do n over d, you don't get a whole number? Like, should we expect a whole number? We should expect a whole number because it's a number of times you are hitting. But instead we get instead we get this. Am I missing something about part 2? Is this not 1 million? I think I found it. I think I found my bug. It's not 1 million. Why did I see that and think 1 million? Okay. Oh my God. 10 to the 13th. Oh boy. Yeah, that's a big number. Okay. It's not mil. It's whatever. Let's call this offset. Or there. Okay, and that is a long. Okay. Now we can go back away from the. Well, let's just check that this works. So wait. Machines 2. Size is 2. So we have 2 that are correct. Okay. Let's go. Man, I should check for things like this more often. So the flipped plus and minus, and I had a failure to copy paste. Yeah, it doesn't tell you the result for part 2. It is. It really is. Okay, so we have 146. We just do that sum. And 2 is that. Okay, and there's our answer. Hi, yeah. Okay, and just over 3 hours. Okay. Finally got it. Yeah. This is me being tired. I saw a big number. I was like, oh, 1 million. It's actually like 1 million squared. Billion trillion is 1 trillion. Thank you. Okay. Well, before we find someone else to raid, probably in Europe, it is late. Yeesh. I lost a lot of time there, but I do have a leaderboard if anyone wants to join. I have some good days. I have some days where I do all right. But these last couple have not been them. I have like sleep to catch up on. So, wait, is this my leaderboard? I'm still 7th somehow. Ian Peter hasn't finished, so once he does, I'm back to 8th. So day 13. Oh, 10 trillion because 10 to the 13th. Okay. Okay, so from 10 to 15, there are a few people that haven't finished this one. I mean, I don't think it was that hard. Like in theory, it wasn't that hard. It's just pluses and minus signs are hard. And copy pasting is hard. It's such a silly way to lose time, but it happens. It should go on my checklist of, oh, are you struggling? Check your plus and minus signs. Um, yeah. Akari in 10 minutes. Wow. And of course, these short delta times are because people just decide to solve the equation first. You swap x and y. That's part of why I use a point class all the time. I haven't had a swapping X and Y mistake in a while because I use a point struct basically. But I don't know. I need more safety rails. Oh, okay, let's make that. Okay, let's find someone to raid. You also use a vector class. Oh, and you still ended up with it somehow? Okay, okay. So, who else in? Let's take a look at Soggy Boy. See what they're up to. Oh, they're back doing day 12. I mean, that was a fun one. Let's see. Why is it defaulting to me? Hex tree in Python. So much am I? See, I was feeling. I like what they're thinking here. Because I was also thinking like maybe there's like a number theory solution here. What language is this? Like I'd done it originally to filter that machines are actually winnable before actually trying to solve it in my brute force solution. Anyone you also have a m dot in front for the current machine object. Yeah. Well, that's why I started just doing that import. You can import the values out of there. That's TypeScript. Oh yes, yes, I can see it now. Um, okay, I like what they're doing, but they don't seem to have a mic. I want them to be able to explain what they're doing. Hey, Rust. I haven't seen enough Rust this year. And they're working on day 12? Yeah, let's do Rust. All right. Well, thanks for stopping by. Thank you, Coder2K, for the raid and bringing Q23 because you gave me back at least an hour of sleep. Extended Euclidean algorithm. Yeah. Yeah, but I don't know, I'm not brushed up enough on math. I would like to read up on that and try like a number theory solution to this. Um, okay. Let's get a raid in. Okay. Well, good luck everyone with the rest of your Avena code. Thanks for stopping by and helping me through my pain. And we'll see you all around. Oh, I don't know if you'll see this, but in case you want to join the leaderboard, you can find me there. And let's start the raid. All right. Good night.